Once we sampled and quantized the signal, let's see how these numbers are stored inside the computer. But before diving into this topic, let's see how information in general are stored in the computer. Well, in the computer, a bit or binary digit is the fundamental information unit of information. It can store just two values, which are 0 or 1. A byte is a group of 8 bits, so it can hold two values for 8 bits. It means 2 to the power of 8 different possible values. That can be numbers from 0 to 255, or simply 256 symbols, such as upper and lower case letters, decimal digits, or funny smiles. And as for any unit of measure, also byte has multiples, allowing to refer to a larger amount of data. Unfortunately, two different scales of multiples exist, and those two different scales are frequently confused also by computer scientists themselves. In particular, these two scales of multiples are the one defined by the International Electronic Commission and the one defined by the International System. Let's see the International System first. If we have a byte, which is a symbol is just a uppercase B, it's made by 8-bit, as we saw. 1 kilobyte is made by 1000 bytes. 1 megabyte is made by 1000 kilobytes. This is the usual international system scale. For example, 1 kilogram is 1000 grams. But usually we talk about kilobytes, megabytes, gigabytes, terabytes, but we truly refer to this other unit of measure, which actually has different names. For example, 1 kilobinary byte is made of 1024 bytes. 1 megabinary byte is made by 1024 kilobinary bytes. So as you can see, it's a different unit of measure, and we often confuse these values with these names. But keep in mind that these are two different things. This is the most used scale, actually, but this is the most used names. Let's help the computer science community by districating this mess, by call this megabinary, gigabinary, and kilobinary, and use this name just to refer as the common values of the international system. So now that we did this specification, let's try to calculate how does a song in a CD quality weight. So we have 4400 samples per second times 16 bits per single sample times 2 channels, because a CD are stereophonic, times 180 seconds, which means 3 minutes on average song length. That means approximately 32 megabytes of data. But wait a minute. Doesn't that mean just 30 songs will drain 1 gigabyte of my mobile internet? Well, that's complicated, because when we store information, there are two ways of storing it. We can store them without compression or with compression. And if we store them with the compression, we can compress in a lossless way or in a lossy way. But let's go with some order. Let's talk about without compression. When we store something without compression, which is the calculation we made before, we just store everything. That string of number we saw when we talked about the digitalization is what is stored inside a computer. So we store every single sample of sound or image or video we convert from analog to digital. In audio, we call this way of storing information pulse code modulation, in short is a PCM. Picture examples of this way of storing data is a bitmap or raw data. There is no example with video because with video files would become huge, so we rarely store video without compression. Other generic data examples are any file. For example, a text file, we store all the symbols without any compression. This compression ratio row tells us the ratio of compression, which is, in case of no compression, 1:1. I mean, we store everything we convert from analog to digital. And the typical use of uncompressed signals is to process them. As we said, if we want to increase the volume of a signal or increase the brightness of an image, we have to multiply each number representing the sound or the image for a certain constant. And doing this with a non-compressed encoded signal, it's quite easy. So this is the typical use for uncompressed signals. With compression, we have lossy or lossless scenarios. Let's talk about lossless scenarios, which mean lossless means without loss. So what is the criteria of encoding something without any loss? It's basically just to avoid redundancy. For example, if we have a picture which is all black but for a single point, instead of storing like we would do without compression, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, and then 0, 0, 0, 0, 0, 0, 0 again, we just store something like please write 100 times 0, then write 1, and then write again 100 times 0. This is a more compact way of representing the same information, but avoiding the redundancy of repeating 0, 0, 0, 0 many times. But without the loss of any information. The information content is the same, it's just packed into a more optimized way. Audio example of these encoding strategies are FLAC or other formats. In picture, we can see run length encoding, which is exactly the example I did of repeating, of telling the computer to repeat a certain number of times. In video example, we have some other lossless codecs, but we have a lossless way of compressing data also for generic data types. For example, the zip or RAR formats, which you probably heard for, are ways to compress without losing any information. The compression ratio is not very high. You can usually, on average, compress something until saving half of the original space. And this type of compression is frequently used for archiving purpose or for a high fidelity fruition of the contents. Why don't we work with lossless coding for processing images, for example? Well, think of that example of the image which is just zeros and white in one point. If you want to put another white point somewhere, you have to take the original image, inflate it, like actually writing all those zeros, then turning one of those zeros again into a 1 value, and then re-encode it. So it will become heavier for the computer to work with the encoded data. So it's better to work with uncompressed data and to store the result with the lossless compressed data. And what about lossy compression? Lossy means with the loss of information. This because the criteria is to avoid irrelevance, not redundancy, but irrelevance. And what is irrelevant? Well, it depends on what you're interested in. For example, if you remember the usual picture of our hearing space, there are certain low frequencies that cannot be heard if not a very loud volumes. So we can represent the signal in the spectral domain instead of representing it in the time domain, and discard all those frequencies that are under a certain hearing threshold. this will save space at the cost of the loss of some information, which is more or less irrelevant because we're not interested in it. But what if we want to manipulate those sounds? What if we want to manipulate the information which has been encoded with a lossy compression? Well, we can do it, but we have a loss of information, and so the quality of our product will be lower. For this reason, lossy compression is used just for fruition or streaming purposes. Typical examples for audio are MP3s or JPEG for pictures or MPEGs for videos. And for other type of data, it depends really on the kind of data you are handling. So back to our example of how much megabytes a song will erode of your internet traffic. This is more in line to what is actually happening, because your song is streamed with a lossy compression, so it will not take so much space as a non-compressed signal. Some notes about lossy encodings. Please never re-encode a lossy encoded file with another lossy encoding. For example, if we have a JPEG and we open it with Photoshop and we retouch it and then we save again a JPEG, it will re-encode the information and you will encounter another loss of information. So just the fact that you are opening a JPEG and then resaving it without any modification, it will actually lose more quality. And this is also valid for audio. If you open an MP3 and just save another MP3 from that MP3, more information will be discarded. So pay attention to work with lossless encoded files or uncompressed files, and just encode as lossy files just once and just at the end of your processing. Video should not be an exception, but working with lossless video is extremely memory demanding. And so, for this reason, 1 or 2 re-encodings are tolerated in case of video. But remember that streaming platforms such as YouTube, Facebook, Vimeo, and others will re-encode your video and pictures when you upload them. And this is also valid for pictures. If you upload an image to Instagram, Instagram will re-encode it into something similar to a JPEG. So consider that uploading your pictures or downloading a picture and then sharing again it will end up in a loss of quality. Here we have an example of what happens when we encode the JPEG just once. You see the nice picture. Well, I don't know if you see the differences, because also this video you are watching is probably encoded a couple of times. So these differences may be lost in encoding. But if you see what I see, which is probably not true, but if you see what I see, you can see here on the left a very crisp picture with nice details. Here we have a zoom of this flower. And in the right picture, we have the same picture, but encoded as a JPEG many times without doing any modification of the picture. Just open and save it as a JPEG, open and save it as a JPEG, open and save it as a JPEG, many times. And we can see that it's really, really messy, especially here in the zoom. You see a lot of details and ripples on the image that were not present in the original image. And also color are kind of slightly messed up. So never re-encode an image many times. So just to recap what we saw in this module, we see what are the unit of measure of computers. We saw the difference between a megabinary and megabinary bytes and megabytes, for example. We saw how things are encoded, so with no compression, with lossless compression, or with lossy compression. And we saw which are the drawbacks of lossy compression, so basically a vertical fall of quality. If something is not clear about these concepts, please watch the video again.